Hello, everyone. This is Team LunaBot's midterm report for the spring semester on our modular lunar rover. The team members consist of myself, Kim, Chris, and Tia. In this presentation, we're going to cover the timeline and milestones for our project this semester, the revised goals and roles, our finances, the progress in our design and its refinement, the physical prototype production and assembly, component testing, as well as next steps for the project.
So for our timeline, we have a little bit of adjustment since we did not receive our EAB reviews by the first day of the semester. We were unable to refine the design between January 13 and 31. So the actual timeline shows that we started on January 15th. And it just pushed a few days until spring break, and then we maintain the same schedule throughout the second half of the semester as planned. Our current milestones include starting the production of the prototype, which we have completed, submitting our Rascal proposal, doing our team check-in, and here we are at March 8th for review and feedback from the midterm report. Following that, we'll have 60%, 80%, and 100% completion between March 10 and April 8th. For our goals, we'd like to design a collaborative and semi-autonomous lunar rover to maintain systems and resources on the moon. Additionally, we'd like to create a modular and scalable design that can be adapted throughout time with changing mission requirements. And if time allows, we'd like to implement machine learning to develop decision-making algorithms and enhance its autonomous capabilities. Darren's role is to find contributors, as in grants, private donors, and scholarships, to fund the project, as well as organize the Rascal proposal packet. And he is our lead engineering technical writer. Kim's role is to inspect all the CAD designs for errors, perform analysis on critical components, and she serves as our lead design engineer with a focus on CAD and GD&T. Chris's role includes assembling the bill of materials, programming the system software, and he is also in charge of routing the wiring. And he is our lead programmer and electrical engineer. My role is to oversee the entire project's progress and to submit documents for Rascal competition, and I am ECE coordinators, conducts stress analysis on critical components and failure analysis, and 3D print and assemble the hardware. And I serve as the project manager and manufacturing engineer. And then we have Rip Molinar, who is there to boost team morale during meetings, and he is our chief engineer of happiness. Our finance situation consists of two different options based on whether we get our NASA selection or not. In the previous semester, we had $500. Now we have a total of $1,000. And our overall budget is $817.85. But we did not account for wiring and breakers in this finance plan, so we do need to add that, which should bring us to about $1,000. In the second finance option, we have accounted for the $6,500 that NASA would provide on top of the $1,000 that we already have. So it includes other complementary sensors and more software that would allow us to have better mapping and navigational capabilities, as well as stronger material selections that would be more suitable for lunar applications.
For the design refinement, specifically for the arm, at the end of last semester in the fall, the arm design had separate brackets because the intent of the model was to be for how you would actually manufacture it, not for the prototype, but for if we were to actually make it. Whereas this semester in the spring, we updated the model to account for how it would actually be made if we 3D printed it. And so instead of having a separate like bracket that would be mounted to the arm, we could actually incorporate the bracket into the arm since we can 3D print more complex shapes. Also, at the end of last semester, there wasn't a final design for how the arm would be mounted to the rover. We knew that we wanted to mount it to the rover, but the actual mounting point wasn't complete. So this semester we added a gear system that will allow it to rotate and act like a shoulder. So it will move the arm up and down, as well as has the elbow rotation, which will allow it to move left and right and rotate.
So to make sure that this design wouldn't fail, we did calculations on the gears that would connect the arm to the actual body. And the first calculations were done using the Lewis equation for bending stress. And then they were later verified in ANSYS. And you can see the three diagrams on the right. The first one is the total deformation. And then we have the equivalent and normal stress. And at the point where the arm would be attached, which is kind of towards the left end, the maximum stress was about 150 psi, which was within the acceptable values for the safety factor and the yield stress.
For the design refinement for the suspension, at the end of last semester, we had a pretty typical rocker bogie suspension with a differential gearbox. As we went into this semester, we realized that we needed a little bit more support from the suspension. So we modified the rocker bogie system and added more mounting points to increase the stability. Also, at the end of last semester, the wheel connectors, the suspension was connected to the motor, and a lot of the force was acting on the pin of the motor. So this semester we modified the suspension mount to the wheels that will incorporate a wheel bracket that adds a little bit of height and also lessens the pressure on the motor. For the wheel connector failure analysis, we calculated the stress at 2 points that we found, or we thought that would be the most critical points. One of them is at the base of the suspension bracket, and then one of them is more in the middle, which we verified that these two mounting points, we verified that the 2 points were higher stress areas through ANSYS, just to confirm that we were looking in the right spot. We used compression, tension, and shear stress equations to then find the maximum principal stress, and it was calculated using the stress tensor. And then we use the maximum principal stress theory to determine the safety factor, which at critical point A, which you can see in the free body diagram, it was a factor of 61. Critical point B was a factor of 67, and the recommended safety factor was 3 to 4. So it was well within that parameter.
Similar to the attachment of the arm to the rover, we had to rethink how we were going to attach the wheel. So as Kim said in the previous slide, we wanted to take pressure off of the motor itself and distribute it on the actual wheel. So we decided on redesigning the wheel component to include a bearing within the wheel that would attach to the motor mounts. And those motor mounts would attach to the bracket. And then there would be a separate bracket, which is the green bracket on the top of the bottom right picture. And that would connect to the suspension. This also allows the wheel to have a little bit more free turning capability, which is always nice. And this design, although it's a lot more components, it is a lot more realistic and it works a lot better than the previous design did. So in our design progress for the photovoltaic system, just a recap of what we completed in the fall, we decided on using a standalone or off-grid PV system, with the ideal panels being multi-junction solar panels due to their radiation resistance. And in case those in space-grade glass, the actual design that this PV system was based off of was a bifacial monocrystalline solar panel, just because those specifications are more easily accessible to the public. And then the power will be stored in a 300 amp hour, 12-volt lithium ion battery due to its weight and its technology readiness. And then in the spring, we completed the wire sizing. And we need to complete the breaker sizing, which we should have done by the week after spring break. For the wire from the panel to the charge controller, we've decided to just use the given leads from the panel, which is a 4-foot 12-gauge wire. From the charge controller to the battery is a 6-gauge wire or an 8-gauge cold temp wire. And then from the battery to the inverter, it's a 14-gauge wire or a 14-gauge cold temp wire. From the inverter to the DC breaker, we'll be using a 4-gauge wire. And then from the inverter to the AC breaker, we'll use a 12-gauge wire.
So we're using a 12-volt battery system to power the entire rover, which supplies energy to all the significant components, including the motors, sensors, and control systems. The drive systems run on 4 brushless motors, each controlled by, there's 2 ESCs to handle the movement of the DC motors. For the precise wrist movement, we're using stepper motors controlled by a DRV8825 stepper driver. This gives us an accurate control for tasks like manipulating payloads or connecting umbilicals. A Freenove spider shield manages the servo motor that control the fingers and hands on the robotic arm, helping to handle the multiple servos efficiently. On the sensing side, we've integrated several key sensors. We have an AI camera for vision tasks, LiDAR for obstacle detection and mapping, IMU for orientation and movement tracking, ultrasonic sensors for short-range object detection. For power distribution, we're using 12 to 8-gauge wire to handle the high currents required by the motors. And 22 to 24-gauge wire is used for the low power signal connections to keep things lightweight and manageable. Finally, we've included an external power supply just for the servo system to keep the power-hungry servos from overloading the Raspberry Pi and to maintain stable voltage during operations. The entire system is powered by a Raspberry Pi 4B running the Raspberry Pi OS along with the ROS, Robot Operating System, which manages all communication between the hardware and software, allowing for modular and scalable control. For motor control, we're using pulse width modulation to manage both speed and direction of the DC motors through the ESCs, giving us smooth and precise movement control. For navigation, we're implementing SLAM, simultaneous localization and mapping, using sensor fusion. This means data from the LiDAR, IMU, and ultrasonic sensors are combined to accurately map the environment and allow the rover to navigate and avoid obstacles autonomously. The AI camera is running TensorFlow Lite to perform real-time object recognition, which supports tasks like identifying objects, docking points, or hazards on the lunar surface. The system is designed to operate in 3 distinct modes: autonomous, where the rover makes decisions on its own; remote is where a human operator can drive the rover directly; and collaborative, where it can work alongside astronauts, responding to their commands or assisting them with tasks. Finally, we're using serial communications between the Raspberry Pi and an Arduino Mega to handle encoder feedback from the motors, allowing us to monitor wheel rotation and ensure precise movement and positioning.
So for the physical prototype production, we have been doing a lot of 3D printing. A lot of the 3D printing that we're able to do at school. So the wheels, wheel bearings, small suspension brackets, arm gears, the electrical housing, camera and sensor mounts, suspension mounts, wheel mounts, and rover stills have all been printed at the school. And then for the other components that are either too big and long running, we've been able to get some external help from friends or my work and they printed the airless tires, which each of the tires was a 36-hour runtime. And then the hand components, I was just able to print at my house. And then some of the other bigger components are just able to get done by other people. The other components that we have so far, the rover body frame, which was, it's made out of T-slot extrusions. The rover body walls, which will encase the electrical components, is made out of 3/16 thick cardboard sheets. And the rover base is a 2-foot by 4-foot plywood. And on the right, you can see some pictures of the 3D prints that we have so far, both successful prints that we'll actually be using in our prototype, and then some other prints that are either printing fails just for various reasons, or pre-prototypes. So prints that we were used to test our final design, we were able to print beforehand. So for the physical prototype assembly, we were able to assemble most of the arm. There's still a couple components in the elbow that need to get printed, and then the shoulder needs to get printed, but everything else just needs to be wired, and the electrical components need to be all set up. And then Tia can talk about the wheel that she designed.
So we did some component testing for the airless tires. We wanted to make sure that we got the infill right, simply because prior to this experience, we haven't been doing much 3D printing using TPU, which is a flexible material. So ensuring that we got the infill to return to its natural shape was very important. The first test tire, we used 30% infill and a gyroid infill pattern. This was decided on because gyroid patterns are typically strong in all directions of stress, whether that's compressive or shear. So that's why we decided on using a gyroid infill pattern. The first test tire is the green one, and we conducted a compression test using a 120-pound load. And the infill was too rigid, and it ended up breaking within the tire, which caused bubbling on the outermost layer. So we had to rethink the infill and the infill pattern, which we decided on 12% with a cross hatch infill pattern. And then we conducted the same 120-pound load compression test, and the result of it was that it was a good balance between flexibility and stiffness. And since it was able to return to its original shape post-compression test, we decided that was the infill pattern that we would use, and we proceeded to produce all of our actual size tires, and we have 6 of them.
We started by installing the firmware and enabling the camera through the Raspberry Pi configuration settings, making sure the system recognized the AI camera and could communicate with it properly. We're using the Pi Camera 2 library to handle the video and feed capturing images. This library provides reliable support for high quality video streaming and still image capture directly from the Raspberry Pi. We've successfully configured TensorFlow Lite on the Pi to handle object detection. This allows the camera to recognize specific objects and provide real-time analysis during rover operation. We've encountered and resolved several dependency and environmental errors throughout this setup, especially common with installing machine learning libraries on the Raspberry Pi. We worked through those challenges and got everything fully operational. Currently, we've successfully tested real-time object detection and video processing, which means the rover can actively analyze its surrounding and identify objects while in motion or during specific tasks. So since it doesn't move right now, the camera works, and all it's been doing is looking at me.
So after all of this, our next steps for the remainder of the semester, of course, we need to continue fabricating it and assemble the final prototype once all the materials are printed. We also will perform additional tests for the brushless motors, the object recognition and mapping, as well as the communication and control between the hand, arm, and vision system working together. And also, we are going to begin working on the proposal for the IMECE submission, as well as brainstorm changes to the design based on whether or not we get selected into the Rascal competition by NASA. And also, we're going to be working with the size breakers and the wires coming out of the breaker box and perform a test run once the rover has been fully assembled. Thank you for watching and listening to our presentation.